Are you guys there?
Yes, ma'am.
Both of you? And evaluation, Usha Sri 82 and Niranjana 86.
Ma'am, I am there, ma'am, but Usha she is having a PI now.
Oh. Okay. Is 58 and 72 roll number are there? Roll number 58 and 72.
Yes, ma'am. 58 is and 58.
72?
I'm not sure.
Okay, Vishal Jaiswal and Ritu Jain. Are you guys there? 144, 106. Kritika and Aishwarya, are you guys there?
Ma'am, Aishwarya here, but Kritika has gone for PI, ma'am.
Very nice. Rishi Satish and Sri Ganesh, 104 and 118.
Hello, ma'am. Yes, ma'am.
Both of you are there?
Yeah, yes, ma'am.
Yes, ma'am, I'm there. You're there.
Okay, fine. So you guys take notes today. Sorry, evaluation today.
Okay, ma'am.
Okay. So we will continue. So we talked about we talked about the evaluation. The uninformed search strategies. We will continue with the next one, which is informed search strategies. Now, this informed search strategy is based upon a concept called as heuristics. Okay, so this is what we talked about. We started with last class. So it is based upon this concept called as a heuristic function. This heuristic function will decide on the efficiency of the algorithm. Okay, so where the goal is already known to you. Okay, the goal, the previous scenario also, you know what is the goal, but you know you have much better information about the goal is also available to you. Okay, so all these are based upon the general approach to the general approach is based upon what is called as the best first search. Okay, that is the general approach. The sense that which node will you expand first? Okay, you will expand the best node first, and that is based upon the goal. Okay, it is not based upon from the source. How do you go from this? It's not dependent only upon the source. It is based upon the goal basically. So in order to do that, you can go in for a tree search, or you can go for a graph search. Okay, in order to do that, you can do any one of these two, and this tree search or graph search will be based upon from the particular node, from the starting node. You will use an evaluation function which will be used for expanding the next node and selecting the next node. So you call this function as f of n, and this function f of n is called as the okay. So this function f of n is called as the heuristic function. H of n is actually the notation for heuristic function, which is nothing but the cost of the lowest path. Okay, the cost of the lowest path from the start node n to a goal state G. Okay, so that is going to be the heuristic function. So in one case, this best first search can probably become something like uniform cost search if you already know where the goal is going to be. So the function heuristic is a function that estimates how close a state is to a goal, how close a state is to a goal state, and it is designed basically for a particular search problem. Okay, so you try to keep moving in a direction that is to be getting you to some kind of a distance. So here you have to evaluate a distance metric. Typical distances are Manhattan distance, Euclidean distance are basically used for doing the paths. This will be typically used in gaming. So we will see again that also. So the general principle is you will go in for a heuristic approach in order to do that. So for example, here you have the start node. This is the starting point and this is the goal state. So if you go in this particular direction, you will get a distance of 15. But if you go directly from here to here, supposing you are able to go, okay, this distance is called as the straight line distance, SLD. That is from the start point to the goal point, whatever is the straight line. If you draw a straight line, okay, you may not be able to go in the straight line, but that straight line is used as a basis for your heuristic function determination, and that is called as the straight line distance. So here, the straight line distance is going to be 11.2 as compared to the previous, the actual distance cost, which is going to be 15 or so. So you have to get your heuristic function such that the cost is going to be almost closer to the straight line distance. Okay, straight line distance, it may not be possible because there may not be a path available from the particular source node to the destination node. So you will decide your heuristic function accordingly. Now let us consider this map. This is what we talked about in the first case where you had the map of Romania. So your starting point is this city Arad, and your end point is this goal state is this particular city called as Bucharest. Now you have to estimate the straight line distance between all pairs of cities. So for example, you consider this city Pitești, okay, Pitești is here. So if you have a path and from Pitești to Bucharest, the path cost is 101, whereas if you look at the straight line distance, it will be 98. So you have to, given 2 points, you know how to estimate the straight line distance. So if you have a lathlon, okay, that is lathlon scenarios, you can use what is called as a Haversine distance in order to Haversine. My handwriting has gone terribly bad. Haversine distance in order to estimate the straight line distance between 2 points. Okay, so you can, because a Haversine distance is basically for class okay, okay. So Haversine distance is basically to estimate the distance between 2 points in a geographical, in a curvature kind of situation. So that is what is Haversine distance. You can use, you call that as a straight line distance. So this basically gives you the straight line distance for estimating between every pair of points. So when you consider this first algorithm called as greedy first search. Now this is again one more heuristic function where we talked about the we'll come back to this example in a minute. Just to give a counter example, and there is you can use heuristic function to do this pancake problem also. So we said we are going to flip the pancakes such that the pancakes are arranged from smaller one to the larger one from top to bottom. So this is going to be your final solution. So you can use some kind of a heuristic in order to, because you know the goal, right? You know what is going to be the goal situation. So you can use some kind of a heuristic function. You will not keep flipping up and down and up and down and up and down. You will just try to use some kind of a logic to flip it up and down. Okay. So that could be your heuristic function to determine that. So there is a one first search algorithm called as greedy best first search. Okay. Now this best first search is based upon the straight line distance. This greedy algorithm is based upon the straight line distance as a heuristic function. So here what happens is you have this straight line distance which is estimated, and okay, so when you're going to expand a particular node, the straight line distance is used as the basis for your expansion. So for example, here you start from this city called as Arad, where you have the goal straight line distance to Bucharest as 366. Now what you do is, Arad's neighbors are Zerend, Sibiu and Timisoara. Okay, Arad's neighbors are Zerend, Sibiu and Timisoara. So I will just mark this as Sibiu and Timisoara and Zerend. These are the three cities which is adjacent to Arad. Now, in the earlier scenario, what you did, you kind of looked at the smallest distance here and then you proceeded. Now, in this heuristic based scenario, you will not consider that. Rather, you will look at Zerend's straight line distance to Bucharest. This is what we talked about as informed search. That is, the goal is already always kept in mind. Then Zerend's distance to Bucharest. Then Timisoara, right? Its distance to Bucharest. And the last one is Sibiu. So Sibiu's distance to Bucharest. Where is Sibiu? Yeah, here. So had it been the uniform cost search, you would have chosen 75. Okay, which is not going to be the scenario. So what you would do is, here you will mark those values here as 253. This is the straight line distance from Sibiu to Bucharest, and this is 329 and this is 374. So you will, it's a greedy, right? So you will expand the node with the smallest straight line distance to Bucharest. Okay, so you will expand Sibiu. So when you say Sibiu, Sibiu's adjacent vertices are Oradea, Arad, this one, Rim, whatever, okay, and Fagaras. So let us call them, so here you will expand, okay, so Arad, but Arad is already a visited vertex, it's okay, let us just expand. Then Fagaras, then you have Oradea, and then you have some Rimniku, okay, whatever, RIMN. So Arad has a straight line distance as 366, okay. Fagaras has a straight line distance as 178. Orad has a straight line distance as 380. And the last one, this one has a straight line distance as 193. So again, you will not look at all those. You will try to expand the one which has got the lowest straight line distance. So this is your starting point. You went to Sibiu and then you have Fagaras. Now Fagaras will be expanded. So Fagaras, you look at it, it has got Sibiu and Bucharest as the two cities. So here, this is Sibiu, this is Bucharest, this is 253, this is 0, right? So this is going to be your final goal state. So you have basically reached the goal state in this particular fashion. So this is based upon heuristic, the straight line distance as the heuristic metric for determining the path from the start state to the goal state. So you are using here greedy, and the greedy is based upon the straight line distance. Okay, so that is one aspect of, that is the first simple algorithm to, first simple algorithm called as heuristic best first search. Okay, but this is not very effective because you need to have the straight line distance for all the nodes, and the worst case time complexity and the space complexity will be order of b power m if everything has to be expanded. So therefore, this is not going to be an effective search algorithm. So you normally go for an alternate. So this is what we have just now shown. Am I connected or not? Are you hearing me?
Oh, yes, ma'am.
No, basically some network connectivity is happening here. Okay, fine. So, so this is what we said, expand the node that seems closest. So we looked at the straight line distance is the metric to expand the node, and then we can look at it. So what can go wrong basically here? You might probably have to expand all nodes, okay? Or if your goal should be known, and so your time complexity will basically be order of B power n. So that is going to be the problem. So in the greedy algorithm, what we talked about is you can expand a node that you think is closest to a goal state. So the estimate of distance to nearest goal for each state should be done as a heuristic. So the common case is best first takes you straight to the wrong goal sometimes, because your goal should be properly done. So that is scenario. Alternately, you might get into a scenario like the depth first search. Okay, so that is probably another scenario. That is why the complexity is order of B power m. Okay, so you might get into a scenario similar to depth first search. Again, this is not going to be always. That's a worst case scenario. You might get into a depth first search kind of scenario where you might end up in a problem. So this is preferred, but it is not very much visible. Then the next search, which was used for a very long time in all gamings and other search algorithms, is this A star search. Now you also have a variation of this A star search called as memory bounded A star, which is called as MA star, or you have simplified memory bounded A star called as SMA star. So this A star search is again, it is greedy only, but it is based upon two functions as against a single heuristic function. So the problem that was discussed by the best first search was that you always looked at the straight line distance from the new state to the goal state. Okay, but the path cost from the source to the new state was not considered. Okay, the path cost from the source to the new state was not considered, in the sense that you always try to expand CBU here, but to reach CBU you have to have 140 on a road basis. I mean, this is the actual cost, but you looked at the straight line distance. So this may not be, so if you probably look at this overall cost, 140 plus 99 plus 211, okay, this is probably 140 plus 99 plus 211 is probably going to be more than 366 as what was discussed by the straight line distance algorithm. So 211, this comes to 310 plus 140. 450 is going to be the path cost from Arad to Bucharest. So you might probably sometimes have an alternate path which is probably not having a good straight line distance, but you might get into I mean, the actual cost might be less than the straight line distance cost. Therefore, it is not good. It is it did not consider that aspect of the algorithm. So in A star search, what you're going to do is you are going to consider two costs. One is G of n, other one is called as H of n. So this G of n is the cost to reach a particular node, and H of n is the cost to get from the node to the goal. So this could be your straight line distance. This is incorporating the cost of reaching a particular node also. So f of n will basically be the heuristic function, the total function, which is nothing but G of n plus H of n. So you are considering the cost to reach a particular node as well as the cost to get from the node to the goal state. So this can be your straight line distance cost, or it could be any other cost which you can think of. So therefore, this is going to be a combined mechanism in order to get my f of n estimated. So for example, given a node n, G of n can be the path cost on an over the long run. It could be a path cost from the start state to the node n, okay, and H of n could be the cheapest cost from n to the goal. So f of n could basically be your straight, I mean, h of n could be your straight line distance cost also. Okay, not a problem because you're going to incorporate both the costs. So that was the drawback in the best first search. So you have to do this in A star search. So uniform cost search, something like a tortoise, and greedy was something like a rabbit. So it looked at scenario. So you are going to combine these two and call that as A star is what is the idea. So here there are two conditions. So you can think of A star as the uniform cost search that uses G plus H. It is the goal, I mean the cost to get out from a particular, the cost to reach a particular node plus the cost to get out of the node together instead of G. UCS uses only G. So A star can be thought of as uniform cost search where it is trying to combine these two costs instead of merely the cost of getting out of a particular node alone. Okay. So there are two conditions for optimality in the case of A star. One is called as the admissibility and the other one is called as consistency. One is called as admissibility, other one is called as consistency. So the first one is called as the admissible heuristic. This is called as the admissible heuristic. Okay. So what it basically does is it tries to not overestimate the cost. Okay, it doesn't overestimate the cost to reach the goal. That is called as the admissible heuristic. Okay. So for example here G of n is the actual cost to reach a particular node, okay, from a current path, and f of n is actually G of n plus h of n. So what happens is there is an immediate consequence that f of n does not overestimate because it is already considering the path to reach a particular node and how much cost can be there to get out of the particular node. So for example, you are here and this is n, and for example this is going to be n dash. So you have incorporated the cost to reach n using G, and you will choose the lowest cost to get out of H. But once you come here to n dash, for example say, the cost to reach n dash is considered in G of n dash and the cost to get out of H of n is also considered. So you are incorporating the cost. So that is called as admissible heuristic, where it does not overestimate. In the sense overestimate is it does not overestimate the efficiency of the cost to reach a particular goal state. The second scenario is okay. The second scenario is basically called as the consistency. This is also called. This is a stronger condition. This is also called as monotonicity. This is a stronger condition. Okay, so this is typically applicable and it is required for A star where it is used in a graph search algorithm. Okay, not for tree search. So you call a heuristic function h of n is consistent. Okay, it is called as consistent if for all n or all n and n dash, which is a successor of n, okay, the estimated cost of reaching the goal from n is not greater than the step cost of getting to n dash plus the cost of reaching the goal from n dash. So that is, it doesn't overestimate in the sense that h of n, the estimated cost to reach n is not greater than the step cost of reaching to n dash plus the goal from plus the cost of reaching the goal from n dash. So here we are talking about adding one triangle inequality. which is similar to, which is very essential for, as far as this A star search is concerned. So where you are saying h of n should be less than or equal to cost of reaching n dash from n using any action plus h of n dash plus the heuristics to reach n dash. Now what is h of n? We said h of n is the cost to reach h of n is the cost to reach the goal state from a node n. Okay, h of n is the cost to reach a goal state from n. And what is h of n dash? H of n dash is the cost to reach a goal state from n dash. So what does it say? The cost of reaching n dash from n, okay, plus the cost to reach n dash, plus the cost to reach the goal state from n dash. If you sum this up, it should be greater than or equal to h of n, in the sense that it could be equal if n and n dash are same, or it could, if you have an alternate path, it should not be where n dash is a successor state of n. So h of n, you should not have come to n dash on a lower cost. Okay, that is, you are saying that at every, and this is applicable for all nodes. Okay, this is trying to prove the correctness of your A star algorithm, in the sense that at every particular point of time, when you are trying to go from one node to the next node, you will consider the path cost to reach that particular node plus the cost to reach the goal state. So you have to cumulatively do that, and when you cumulatively do that, you should not overestimate, or rather you should not basically exceed the capacity. In the sense, for example, you have a, no, this is your starting point. You are somewhere in the middle. Okay. Till this particular point, your estimation of reaching the goal will basically be, for example, 300 kilometers or whatever. Okay. That is to reach the destination is good 300 kilometers. After that, it should not be 250 kilometers. Okay. It will probably be greater than or equal to 300 only, because you have estimated as 300 kilometers. You may not have the direct straight line distance. Therefore, you can basically be more than that. So your estimation should be correct is what we are trying to look at it. And this will not go wrong because you are going step by step, because you're looking at every node as a successor state of the previous node. Okay, and the previous node, the starting point will be the starting node, and when you go to the next node, you have to obviously go in the go in a consistent fashion. So you can say that every consistent heuristic, this is called as consistent heuristic or consistency or monotonicity. Every consistent heuristic is admissible. Now what is admissible? We said that admissible is it doesn't overestimate. It tries to give the actual estimate of a particular problem state. Now let us look at the same example whatever we have done with respect to the Bucharest problem to reach Bucharest from that city. So how does A star behave? Okay. So again, you have to start from Arad. Okay. Again, you have to start from Arad. But here it is G of n plus H of n is going to be your heuristic. Now G of n is what? G of n is the cost of leaving that particular node, okay, reaching that particular node, and H of n is what? The cost to reach the goal. Okay. So I will rewrite here. G of n is cost to reach n, and H of n is cost to reach goal. So you are in Arad. So the cost to reach Arad is 0 plus H of n is, you are going to use a straight line distance. So H of n is 366. So you will say 0 plus 366 is the overall f of n for Arad. Okay. Now you have to expand. Arad has got three neighbors. One is Sibiu. Okay. Other one is Zerend and Timisoara. Timisoara and Zerend. Okay. Now I have to estimate f of n for all these three nodes. Now, what is g of n? Cost to reach n. So Sibiu can be reached from Arad in 140. So this is 140 plus. Similarly, Timisoara is 118. So this is 118 plus. And Zerend is 75. So 75 plus. Now what is the h of n? H of n is the cost to reach the goal. So the cost to reach goal will be Sibiu is 253. Timisoara is 329. And Zerend is 374. So you will estimate this function. So this comes to 393. This will be 18, 27, 47, 447. And this is going to be 449. Okay. Out of these three, Sibiu is the shortest. Okay. So you will expand Sibiu. Okay. So when you expand Sibiu, Sibiu has got Arad, Fagares, and Rimnu. And Oradea. Oradea and Rimnu. So what happens actually? So this is going to be the cost. So consider Sibiu to Fagares. Okay. Sibiu is 140 is the path cost. Okay. So Sibiu to Fagares, I'll just mark this 9980. This is 140. This is 99. This is 80. This is 151. And the previous one is 140. Okay. So the cost to reach this particular scenario is 280. The cost to reach is 140 plus 99, 239. The cost to reach this is 291 and the cost to reach this is 220. This is your g of n. Then you have to add the straight line distance here. So this is 366. We already know, right? We have been doing that. So Fagares straight line distance is 178. Oradea straight line distance is 380. And 193. So if you do that, this will be 646 and this will be okay. So this is 17, 11, 417 and this is 117, 671 and this is 223, 413. So 413 versus 417. So you will expand this node. So what did we expand in the previous algorithm? We expanded Fagares there. Now we are expanding this one. So it's going to be a change. So this will be expanded. So when you say Rimnia, its adjacent vertices are Pitosti, Craiova and Sibiu. So you can expand that again. So Fagares will be costlier. I'm not going to calculate that. So then you have Pitesti, Sibiu. Sorry, Sibiu will be costly. I'm not going to calculate. Sibiu, and this is Craiova. Okay. So Rimnew has got 1, 2, and 3. I'm not going to calculate this. These two I'll calculate. 97 and 146. 97 and 146. So it is 220 plus 97, which is 317 plus. This is 220 plus 146, which is 366 plus. So 366 plus Crayova's straight line distance will be 160. Pitesti's straight line distance will be 98. So this is 98. So obviously this will go ahead. So you have to go in this particular direction. So Pitesti will be expanded and you have Bucharest, which is the next neighbor. So from there, if you consider Pitesti, Pitesti's neighbor is Bucharest, Craiova, and this one. So this has 101. It's already a goal state, right? So h of n will be 0. So only 101 plus this will be considered. So Pitesti is here. Its neighbor is Bucharest. This is 317. So 317 plus 101. 317 plus 101. This is 101. Okay, so 418 plus 0. That will be the cost here. Anyway, this is a goal. You have reached the goal. The next city will be again. Obviously, this will be the smallest. So others cannot be the smallest because h of n becomes 0 here. Okay, so this is how A star basically works. So it uses two functions. F of n is equal to g of n plus h of n in order to do the correct in order to solve the correct algorithm. So it uses the cost to reach a particular goal state and then the cost to reach a current state n and the cost to reach the goal state from n. So both will be considered. Now h of n in this example we have used HSLD, which is the straight line distance parameter. Okay, so this is what is explained with another small example here, but we have just done a bigger example itself. So you can just take a look at it. It is combining UCS and greedy. That is what we have been talking about. So UCS looks at only the cost to leave a particular node. Greedy considers the cost to reach a particular goal. So now this is a combination of both, and this example is what we have seen with respect to the Arad example itself. So this is what we have said. So when should A star terminate is a question. So should we stop when we NQ a goal, or should we continue to find an alternate possible path? So normally that is where the problem comes into picture. So here we normally stop when you come to a goal state. Okay. So supposing if it is a cyclic graph, then you probably have a issue of going back and forth because it keeps accumulating. The cost to reach a goal state keeps accumulating, and this is going to be the problem of a graph applying A star to a graph basically. Okay. So because here the actual bad cost will be less than the estimated good goal cost, therefore you keep circling if it is going to be a graph algorithm. A star works good if it is going to be a tree search, and you can expand all possible nodes, and that will be a good algorithm to expand. So here we said admissible heuristics, idea of admissibility. We already talked about this. So it is inadmissible. It's called as pessimistic heuristics, where you break the optimality by trapping a good plans on the fringe. So that is not to be done. Admissible heuristics slow down bad plans but never overestimate the cost. Okay, so that is the consistent admissibility policy. We have talked about this. So this is just stressing the point still further. A heuristic H is admissible if h of n is lying between 0 and h star of n, where h star of n is the true cost to reach a particular goal. Okay, so whatever heuristic you're considering at a particular point of time should be less than or equal to h star of n. This is exactly what he said. H of n should be less than or equal to cost of reaching n dash from A plus h of n dash. Okay, so the same thing is done here. So optimality of A star search, it is optimal. So here, supposing say A is an optimal goal node and B is a suboptimal goal node, H is admissible. A will exit the fringe before B. Okay, so that is A will be in the fringe vertex, but once A is reached, A will be out of the fringe vertices. So therefore, you will always get the optimal goal node only in your A star search. So imagine B is on the fringe. Some ancestor n of A is on the fringe too. Okay, so n will be expanded before B is the claim. So what happens is if f of n is less or equal to f of A, that is a one possibility. Then f of n is equal to g of n plus h of n. So definition of this is what I just now told you with respect to you are starting from a particular point here, you are reaching the middle here. The cost of reaching that will be definitely same as the other one. So you are always ensuring that there is optimal of A star tree search. Again, graph will be a problem as far as A star is concerned. So this is the definition of admissibility of H. So you will read the cost to reach A will be greater than or equal to f of n. So therefore you will come to this particular situation. F of A is always less than f of B because it's at a different position than this one. So you will be encountering only this node before you encounter B. That is what is the proof. So properties of A star. Yeah. UCS versus A star contours, uniform cost expands equally in all directions. A star expands mainly towards the goal but does hedge its bet to ensure optimality. So uniform cost search, we have already seen that it tries to, it doesn't know the goal exactly, in fact. So it finds whether it has to check whether have I reached the goal state or not should be checked at every particular point of time. Whereas A star always keeps in mind the goal state and therefore it basically goes for optimality. So this is just a comparison of greedy, uniform cost and A star. So greedy search from here to here, you can try to expand all possibilities to come to this. Uniform cost search, there is a possibility that depending upon what nodes you expand, okay, now it is not, the cost is different. So you can try to expand in all possible directions and finally you might go through the complete setup in order before you reach the goal state. Whereas A star is targeted, okay, towards the goal. So it might have gone to this area as shown here. Okay, there's a possibility, but still it will reach the goal state. Okay. So A star applications, as I said before, initial scenarios, many video games, pathing, routing problems, Google Maps also was based on this only. Hello. சொல்லுங்க சார். 11:30 சார் வந்துடுறேன் சார். Okay sir. Okay, thank you sir. So you can find application in language analysis, machine translation, speech recognition, everything. So when you look at machine translation or language analysis or speech recognition, in order to find the next word, which direction will I basically go forward? For all those things, you can try to go with A star search kind of mechanism. So robo motion planning, all these are based upon A star search only. So these are just another scenario. So you can actually solve the 8 puzzle game using the A star search. So what are the states? How many states are there? What are the actions that you will basically go? how many successors from the start state, what should the cost be, all these things you can do this as an implementation. So you can, tomorrow's class, you can implement A star search for solving the 8 puzzle game. Or you can solve this for the traveling salesperson problem. Okay. I know it's a graph, TSP is a graph, but still you can, it's suboptimal, its solution will be suboptimal, but you can, you can get to that particular situation. This is an example. So here, 8 puzzle heuristics could be number of tiles misplaced. So why is it admissible heuristics? In the sense that it is not going to be overestimating. You can just go up or down, etc. So all the blocks are misplaced. Okay, so that's why head start is equal to 8. Okay, so you can try to expand the nodes and then try to get to this problem. You can have another distance called as Manhattan distance, otherwise called as city block distance. Okay, which is just the sum of all the edge cost. That is called as Manhattan distance. So, okay, so just this is just an example, you can just take a look at it. Okay, I'll stop here. Tomorrow we will see, the next class we will see the modified A star and then get to the scenario. Okay. Hello. Sir, இந்த letter ஒன்று அனுப்புவாங்கன்னு சொல்லியிருந்தாங்க சார்.